Now we're going to free up our little rotating object and let it rotate freely in space. So to a physicist, this problem is called a rigid rotator. It's a free rotator. And to set it up, the first thing we need to do is get our spherical coordinates straight. So here we've got the x, y, and z Cartesian axes in space in 3 dimensions. And what we're going to do is, first of all, define some position by, instead of x, y, and z, the 3 variables are going to be the radius away from the origin, an angle phi, which is basically the longitude, which is also the azimuth is another term for it, and that's going to be the angle away from x, projecting this location down into the xy plane, and this is the phi we've already seen, and then the sometimes called the colatitude or the zenith angle is going to be theta, coming down from the z-axis. So an angle of 0 means we're pointing straight up, theta equals 0, and an angle of pi over 2 or 90 degrees means that we're in the xy plane. So these are the spherical coordinates shown in purple here. Now, for this problem, the rotator is fixed, so our mass m at the end of the radius vector r is sitting there on a rod, basically. So r is fixed, and the only variables we have are theta and phi. So it's basically a 2-dimensional problem, though the thing is spinning in free space. And once again, we have a moment of inertia, I is going to be equal to mr squared, but we're going to see how that actually comes out of the math in a little bit. And to give this some physical representation, the system, the chemical system, the molecular system that this is consistent with is a diatomic rotator where we have 2 masses, think 2 atoms, separated by some, the mass m1 and m2 there, separated by some bond length r. And it's rotating. It has to rotate perpendicular to the bonds, and the rotation is, the amount of rotation is one of the things that we're interested in, but we're also interested in what's the angle of the whole system. So it's spinning around, but it can be spinning around kind of any which way in space, and so that angle becomes a matter of interest as well. Now, the mass 1 and mass 2 are not the same as one mass sticking out at the end of a fixed length r. Those are slightly different problems, and it turns out that we can express the mass in terms of a thing that we call a reduced mass. We're going to derive this a little more in a couple of lectures, but it's a good place to start introducing it. And so basically, we call it mu, and it's just the product of the 2 masses, m1 times m2, divided by their sum. And once again, the moment of inertia now is this reduced mass mu r squared. So it's like we have a single mass in the left-hand spherical coordinate setup, m, out at the distance r, corresponding to the bond length. But instead of that one mass value, we get this reduced mass. And the thing to notice, first of all, so there's a product and a sum of masses when we get this. And you gotta put the product in the numerator because the units have to work out to be mass. That's the basic, super important way to remember this. So I've got a product, I've got a sum, and I need to end up with kilograms of mass units. And so my product's got to be in the numerator because I have mass times mass divided by mass gives me mass. Never, ever, 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 ever put that product down below in the denominator because you would get inverse mass units, and that doesn't make sense. So you want mass times mass divided by mass equals mass. Now it's always useful to think of the 2 limiting or some limiting cases for something like this. So let's look at one case where the 2 masses are the same. So what we call a homonuclear diatomic, H2, O2, N2, those things. If those 2 masses are the same, then I have mass squared divided by twice the mass, and the reduced mass is just half of either of those two masses. So the reduced mass mu is 1/2 of the mass m1. So the other possibility is that, let's say, mass 1 is really, really light, and mass 2, atom number 2, is really, really heavy. Think HCl, Hi, a very light mass and a very, very heavy mass. In that circumstance, the sum, m1 plus m2, is basically just m2. So I have m1 times m2 divided by m2, and it just comes out to m1. So the two limiting cases are pretty useful. The reduced mass is always somewhere between half the lighter mass and the lighter mass itself. So it's actually kind of limited. You look for the lighter of the two masses, and the reduced mass is going to be somewhere. It's no less than half of that lighter mass, and then it sort of sneaks its way up toward being equal to the lighter mass. So basically we have the lighter mass spinning around, orbiting, if you will, the heavier mass. But when the two masses are equal to each other, it becomes a little more of a pair dance, and the reduced mass goes down a little bit from either of the masses. But it's somewhere between half of the mass, the lighter mass, and the lighter mass itself. So it's actually pretty tightly bounded there. Now we've got our rotating object in free space. We've seen it can be a diatomic. We know how to set up the reduced mass. We know what the moment of inertia is. So as always, the way we start any of these problems is to say, let's solve the Schrodinger equation. Let's find out the wave functions, the eigenfunctions of the Hamiltonian of total energy of the Schrodinger equation, and let's find out what those energy levels are. So that's the basic question. What are the energy levels for this system? So to set up the Schrodinger equation, it's always h psi, but now that it's a function of theta and phi, is equal to E psi of theta and phi. And the question is basically, what's h? What's the Hamiltonian for the problem? Well, h is minus h bar squared over 2m times the second derivative, the Laplacian, now in spherical coordinates, and there's no potential. We don't have any, aside from the fact that this thing is doomed to forever rotate in a circle, in those coordinates theta and phi, it's a completely unconstrained rotator. So it's just a second derivative. The only issue is that second derivative, the Laplacian, is a wee bit involved in spherical coordinates. So the actual value of the Laplacian in spherical coordinates in general is this ugly expression here. And it's just long. You can look up the book Div Grad Curl and all that to actually work your way through it if you want. But if we look at it here, there's basically lots of things that look more or less like a second derivative. There's a partial by partial r squared d by dr. There's a partial theta, sine theta, d by d theta. And then there's actually something that looks a lot like a second derivative, the d squared by d theta squared, d squared by d phi squared there. But they're all kind of tied together because unlike the nice clean Cartesian coordinates, the distance you travel, which is if you change a coordinate, you're changing properties of kind of all the other coordinates at the same time. They're kind of linked together. So you see sine thetas all over the place. There's r squareds all over the place because everything depends on how far out you are. But in this case, we can kind of rework it a little bit and say that I've got this radial part here, 1 over r squared d by dr of r squared d by dr, and then there's a 1 over r squared in all of those terms. And so then the angular term I'm going to call lambda squared. Instead of this del squared, we've got a big capital lambda squared. And that thing we call the Legendrian. And it's 1 over sine theta d by d theta of sine theta d by d theta plus 1 over sine squared theta d squared over d phi squared. So there's a sign issue there all the time. And the reason why we're pulling this Legendrian out is because the r is constant. So all those dr parts in the Laplacian, in the second derivative, go to 0 because we're not allowing the radius to vary anyway. And so the Legendrian, the angular dependence of the second derivative, is the thing that, that we're working to solve here. When we get this thing going, we now have the expression minus h bar squared over twice mass times the Laplacian of the wave function, psi of theta and phi, equals energy times the psi of theta and phi. That's our Hamiltonian, that's our Schrodinger equation. And another thing here is that we have a new operator. We introduced that Legendrian, and to make it something that's a little more physically meaningful, we can define an operator L squared. See the little hat, big L hat squared is just minus h bar squared times the Legendrian. It's got a hat too because it's an operator, and that capital L squared is the square of the total angular momentum. The square of the total angular momentum is actually something that's relatively useful to keep track of, and so we'll use that operator a little bit later. But now we can convert our Hamiltonian Schrodinger equation into the actual things that are varying. So the h bar squared over 2mr squared times the Legendrian of the wave function equals the total energy times the wave function. And notice that mr squared in the denominator there. Mr squared is the moment of inertia, and also the wave function psi of theta and phi. Once again, we're going to use this separation of variables, and so psi of theta and phi we're going to call big theta times big phi. So big theta is a function only of the angle theta, and big phi is a function only of the variable phi. And this is this hopeful conjecture that we hope will lead to a successful separation of variables. So now we get the Schrodinger equation is minus h bar squared over twice the moment of inertia, 1 over sine theta d by d theta of sine theta d by d theta, chugging away on the wave function big theta big phi, plus 1 over sine squared theta d squared by d phi squared, munching on big theta times big phi, is equal to the total energy times big theta and big phi. It's a big long expression, but all it is a curviness, a curvature operator, munching on a wave function equals the total energy times the wave function. It's our Schrodinger equation. It's just the spherical coordinates get a little bit snarky. But basically, after a lot of work, I can push and pull and divide and move things and whatnot, and I get an expression on the left-hand side is a bunch of stuff which is a function of the variable theta and the energy. And that's equal to an expression that looks like the curviness of this function phi, big phi. So the second derivative, partial derivative, d squared of big phi over d of the variable phi squared divided by the function big phi. And those have to be equal to each other, and by the argument we gave last time, when you have this situation where there's a function of one variable equal to a function of another completely independent variable, the only way that can be true is if they're both equal to a common number, the common value, which is the eigenvalue in German. And in this case, it's useful to call that number minus m squared, or minus m sub z squared. I'm going to use the coefficient z here to, again, make sure we don't confuse that with a mass, and it's going to wind up being a z component, so we're going to use m sub z as this. So first off, the right-hand part of this, the curviness of this big function, phi is equal to minus mz squared. That's just slinky. That's the same function we've been looking at. It's the same function we solved for the two-dimensional particle on a ring. So big phi is just e to the I m sub z phi. So big phi is slinky. We know that function. We know it well. The left-hand side is a much more complicated expression. Here's what it actually looks like. sine theta divided by big function theta, d by d theta, sine theta, d by d theta, munching on big function theta. And then I get a 2I over h bar squared energy times the sine squared of the variable theta minus that mz squared is all equal to 0. And that's a big complicated expression, but that's one where the mathematicians say, ha, that's a known problem. And we could work through the solution in applied math, but it turns out that the answer to that known problem is the big function, big theta of the variable theta is equal to a thing called p. It's a polynomial p, which is the exact polynomial depends on two index integers, L and M sub z, and it's a function of, what we're going to do is put in cosine theta. So p is a function of x, but we're going to replace x with cosine theta wherever we see it. Also, the number 2I over h bar squared e that you see there, that actually has to be equal to this counting index number L times L plus 1. It's the only way the problem gets solved. Those are eigenvalues, right? And L can be any integer, 0, 1, 2, 3, etc., up to infinity. So this function p, that is what we call an associated Legendre polynomial. So if you're going to look it up on Wikipedia or in applied math books, these guys are a very famous set of equations called the associated Legendre polynomials. The other thing is this value m sub z. The function can also only be solved in a useful way for this problem if the absolute value of that index m sub z is less than or equal to L. So L can be anything it wants. It's an integer, but it can be any integer it wants. But once L is established, that second index m, that has to be less than L in the absolute sense, the absolute value. So it can be a negative number, a 0, it can be a positive number, but it can't be any bigger than L. And that's actually what makes them associated. If m sub z is 0, then you get the Legendre polynomials. The m sub z is not 0, you get the kind of extra bang for the buck. And even though we say this is a known problem, it's actually, there are equivalent known problems that define sine and cosine and everything else. They're all actually defined in terms of these differential equations. So it's just some solution to the differential equations. And like all of these eigenvalues, it turns out that the thing only solves when there's certain associated integers that meet certain conditions. And these are the eigenvalues that lead to the quantization that makes quantum mechanics be called quantum mechanics. These solutions are actually quite famous problems, and they're called spherical harmonics. So we're spinning in a spherical coordinate system. We're breaking the problem up into a whole succession of bits, and that's called a harmonic analysis often, or a frequency analysis. So that comes together, they're called spherical harmonics. And basically the wave function psi of theta and phi is equal to this function that we call big Y, and then we got this funny subscript L superscript m sub z of theta and phi. And that in turn is equal to these associated Legendre polynomials p sub L super m sub z of cosine theta times slinky, times e to the I m sub z times the variable phi. So you get a fairly concise set of functions. We'll look at those functions in the next video. But there's some function, some value. I see slinky lurking in there, and then these polynomial things. We only get solutions where we have two quantum numbers now. Quantum number L, the principal quantum number, is 0, 1, 2, 3, etc. One of the characteristics of the principal quantum number is it can basically always be just about anything it wants. It's high on the pecking order, and its victim lower on the pecking order is now the quantum number m sub z, and that's equal to negative L through 0 up to L. And notice that there's L values below 0 the value at 0, L values above 0, so there's a total of 2L plus 1 values of M sub z for any given value of L. The actual energy levels here, the thing we really want to know in a lot of cases, are the energy levels just h bar squared over twice the moment of inertia times L plus 1. So once again, just like the particle in the box, just like the particle on a ring, the energy goes like quantum number squared, but it's got this little plus 1 in there. Little plus 1 actually matters a lot, as we'll see in a second, but still it's an h bar squared that's often associated with the energy divided by twice the moment of inertia times L plus 1 times something like quantum number squared. Also, the L squared, the total angular momentum squared, that's just h bar squared times L plus 1. So the angular momentum does not have the moment of inertia in it. It's just raw units of h bar, as always. The angular momentum itself, the absolute value, is equal to h bar, the raw units, times the square root of L plus 1. And the z component of that angular momentum, how much it's spinning around the z-axis, which means the rotation within the xy plane, if you will, is just h bar times this quantum number m sub z. And the other thing to notice here, so we have angular momentum is coming out in units of h bar as promised, but remember m sub z can't be any bigger than L, and that little plus 1 is really important because the square root of L times L plus 1 has always got a little bit extra because of that plus 1. And so there's always a little, I can have most of the total angular momentum expressed within rotation in the xy plane, if Lz is as big as it can be, which is when m sub z is equal to plus L or minus L. But that little plus 1 there means I never quite get it all. And that little bit extra is one of these things that's always in quantum mechanics. There's always this little bit of fuzziness, the uncertainty principle, where I can't quite specify everything about the system perfectly. And once again, that Heisenberg uncertainty principle kind of crops up. So that little plus 1 is really vitally important because it gives it just a little bit more. But still, the angular momentum winds up being expressed in units of h bar, and thus it can exchange from molecule to molecule.